Okay. Yeah, it's our pleasure to have Fengdi to give a talk about reform, reducing human error in scalable formal software verification with reinforcement learning in language models, a preliminary study on Dafny. Fengdi is currently a PhD student at University of Alberta with Rupam, Dale, and Chaba. Yeah, I call them first names as actually I'm pretty familiar with those people. So yeah, I got my PhD from Alberta too. And yeah, many people may know this year uh, Professor Lee Sutton in Alberta got the Turing Laureate, Turing Award. Yeah, Fengdi yeah, is working on, yeah, actually she has several very good read papers and now she focuses on software uh, verification with language models. And she also gave a triple I tutorial on triple I 2005, right? Yeah. Yeah,
Right,
so
2025.
25, yeah. Oh, yeah, 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 yeah. Yeah, yeah. So, yeah, without no further ado, so yeah, let's welcome Fengdi to give the talk. Thank you.
Thanks for the introduction. Thanks for the organizing. Today, this talk will focus on how to scale up large language model training plus RL. This work focus on formal software verification. It's done by very cool team led by Dr. Jie Fu from Shanghai AI Lab. Um, and considering I'm from UL Alberta and my background, I will try to talk about it from a RL perspectives. 1 second. I will try to make a comparison with traditional RL tasks. Like previously, we focus on games, Atari games or Mujoko, and usually there is a simulator given. Also, we each time we only solve one task. The optimal strategy can be summarized by 1 or 2 sentences for Atari games, and for Mujoko, the dynamics, the underlying true dynamics can be captured by 1 or 2 ODE equations. And this project focus on code to specification generation. It given a code, it try to output formal specifications which describe the code behavior. For example, just on the right-hand side, we show some specifications labeled in green. Like this ensure, it tells us what the output should satisfy, what property the output should satisfy, and invariant, what property should always be held during the loops. And when we want to do RL training on this code to specification generation task, we see some difference from the traditional RL. Like there is no simulator anymore, and it's not working on a single type of task anymore. The code itself contains all kind of data structures, sorry, all kind of algorithms. It requires a very diverse range of detection process. And given these differences, what can we borrow from traditional RL and what elements are missing? That will be a key focus of this talk. Just wish we can have some open discussion. This talk will start like with the motivation of this code to specification generation task and show some empirical result from our paper. And then we will start this open discussion. And I cannot really see the chat during my presentation. So let me see. Maybe you can just maybe you can remind me if anyone has any question.
Yeah, yeah, no problem. Just yeah, no problem. Yeah, just now the problem I think I can answer, so I won't
Yes.
give interrupt.
Um,
Basically ask about the the clarification problem about what's software verification.
yeah, you will know that very soon. So what is formal verification? Let's start from this question. it's a way to verify the quality of the code. Previously, people rely on union test, like after writing a code, we write out some input, and for binary search, we will know what the output should be, and we write out those union tests. And here we have a code about binary search given, and we try to write some union test, and it passed all the union tests, and the code is accepted. However, it actually has a bug, but it's still accepted. Why? Because union test is not a way to guarantee the code quality. The code can fill in uncovered areas. How to write union test will be a very tricky thing, and it gives big workload. Like for lead code questions, usually it's just 10 lines, like 1,000 lines of code. However, it already requires like almost 100 unit tests. And if we want to scale up, we want to go to 1,000 lines of code, there will be a dramatic increase in the amount of union tests needed. On the other hand, formal verification, it directly, given the code, it write out what the output range should be for any input. Like here, as we say, ensures, it write out some properties about output. And then we can pass it to a mathematical verifier. If the code, the specification is verified, then we know just those post conditions, our requirement will always be held for no matter which input. So the code quality can be guaranteed in this case. That's why we maybe prefer formal verification to union test when we want to scale up coding, just to scale up the length of our code. And here we adopt Dafny, which is a language, have just a verifier given. Our final goal is to build a verifiable coding agent, like given the user query in natural language. The agent can generate formal specification and the code at the same time. And then the agent can ensure the equivalence between all these three key components. That is, the specification formally describe the query intention, and it captures all the code behavior. And this ensures the code exactly fulfill our intention without any extra behaviors. And then the equivalence between the specification and the code can be checked by a verifier, like the one given in Dafny. It can be checked mathematically. So when it passed the verifier, we know it's definitely correct. This project focused on a small edge of this verifiable coding agent. We just want to say, okay, can we just go from code to specification for now? And this task is itself very interesting for general purpose. It's very similar to code I/O test, where a code is given, input is given, and the large language model is asked to predict what the output should be. And people have proved that if a model is pre-trained on such code I/O data, it has an improvement in its general reasoning ability, even on natural language or math reasoning. And our task is like, you are not predicting the output for one input. You should predict the output behavior for all inputs. And this kind of task just require general deduction ability. So that's another reason motivate us to do the code to specification generation. Okay, that's the generation part. Hope you already know what is formal software verification. And let's go into the methodology. We mentioned that we want to scale up large language model plus RL training. And one thing is to reduce our reliance on human data, on human priors. So we already know that we need a huge amount of data for training. And if this data is always annotated by human, then it limits the data amount we can get. That's why people are saying that, oh, we are running out of data. So what we propose is that we should synthesize our own data. It includes the input, output, and COT. So input, just given our task, it's just the code. And for the output, it's like the specification. And just none of them should rely on human creation or human design. And the second thing to scale up is we need an auto evaluation signal. Like when we go to tasks without human annotated data, how can the agent know the solution is correct or not? We need some auto evaluation thing to tell to help the agent to make the judgment, and then it can continue improve itself. Then given this large amount of synthesized data, this auto evaluation signal, then we can just use RL algorithm to train the agent to learn from its own experience to reinforce good behaviors. That's the pipeline, and let's go into details. So we mentioned that for the synthesized data, we need to synthesize the input first, and which is the code. What we do is we first transform, and as we mentioned, we use Dafny to verify everything. So we need to have code written in Dafny. So first we directly transform current Python code into Dafny. And then we try to synthesize our own data by recompose functions, methods in the code. And then for the solution, we ask Cloud to generate corresponding formal specifications. And we call them ground truths. But Cloud is actually very bad at doing this task. Their formal specification is far from fully describing the code behavior. And the last thing is we do not want to have human annotated reasoning trees. So for this work, we just have no COT at all. We just say human annotated reasoning is not a scalable way, and also maybe it's not the right way. Maybe we shouldn't anthropomorphizing the thinking path. And then we go to the auto evaluation thing. So we mentioned that for formal verification, we want to verify if the written specification is mathematically correct. And in the math world, we have axioms, we have theorems for each statement. There is a correct thing, there is a correctness thing. It's for each statement based on the mathematical axiom and theorem. It's either correct or wrong. And this correctness of formal statement just gave us that auto evaluation signal. But which statement should we verify in the math world? Just which become the question. What do I mean here? Like at the beginning, we just say, we just use the correctness of our formal specification as reward. But we suffer from some reward hacking. Here is the code, like it asks us to find if P is in the grid. If it is, return the position of P. If not, return -1. And if we only want to say, oh, write correct formal specification, then the agent just write out some very trivial thing, just to say the position should be between -1 and the size of grid. And apparently it is correct, but it's not really capturing the behavior of the code. So even we have that correctness of statement thing as the word signal, we need to think a little bit about the reward design. Then we switch to check the correctness of another statement. We want to check if the generated specification is stronger than the cloud generated. Stronger, this is a partial order defined by us. It just to say JT here means the cloud generated specification. and GEN represent the one generated by our agent. Pre just means the precondition. Precondition just describe the input range, input domain. And we say as a wider range of input is better. Just it means the code is adaptive to more inputs. And then we say the post conditions should be stronger. Says like the output range should be smaller. The algorithm, if the specification gave a narrower output range, it more precisely describe the code behavior, then it's better. So that's what we check. If the precondition is weaker and the post condition is stronger, this can be checked by written out a formal statement, like if generated post condition can imply the ground truth post condition. If it can imply the ground truth post condition, it means it's actually stronger. It's a stronger statement. And so instead of verify the correctness of specification, we go verify if this implication statement is correct. Just check whether we generate stronger specification than the ground truth. And this one turns out to work. We can see here for this example, the ground truth only capture the case where P exists in the grid. It require if we see the ground truth on the fourth line, it require P to exist on the grid. However, just what our agent generates is in the below. It says it removed this requirement. It gave a looser requirement, and it says when P does not exist, then position should equal to -1, and gave a stronger post condition. So we can see that even we are making a comparison to the ground truth, it's not supervision learning. It's still open-ended reward. And in this case, our generated specification just surpassed the quality of the ground truth. And then there are some empirical results, like after our RL training, we can see some improvement from SFT. SFT is shown in the blue line. RL is shown in the orange and green line. And the x-axis is just the number of rollouts. Like for each question, we ask the model to generate 128 solutions. And as long as there is one rollout gave a correct answer, we say it's 100 just at rollout 128, just as long as there is one rollout gain the correct answer, just this question is marked as correct. It gains the accuracy metric. Yes, exactly. Yes, pass at n. And right now there is a debate going on about RL. Like people are saying maybe it's just a compressing pass at n ability to pass at 1. And our result just answered this question very positively. RL is indeed pushing the boundary of SFT. And then we also question just where does this ability improvement come from? We measure some exploration score. On the left hand, we just measure if there is novel specification generated. By novel, we mean it's never covered by SFT. It's never covered by ground truth. And about 20% of data have some novel spec generated. And also those specification just had some meaning. It's not trivial. It's not like ensure true. Just 20% of data generate novel, effective specification. On the right-hand side, we measure some diversity score. We embed those specifications into a continuous space. and we measure the distance between generated specifications. The orange line is the RL result, is our RL result, and the blue line is the SFT result. And our RL just define a larger space in the continuous embedding space. It also means it covers more specifications than SFT. And this good exploration behavior is positively linked to the performance improvement. We do some statistical analysis, and this exploration lead to the performance improvement. Also, we can see this exploration ability come from tool regularization, which is entropy maximization and KL regularization. Basically, we figure out just the entropy maximization can give us the exploration, and adding KL can further improvement the performance a little bit. As mentioned before, we have our tasks transformed from Python code first, and then we try to synthesize our own code. Here, our model is trained on code transformed from Python. We call them in-domain. For those synthesized data, we only have 300 data, and we call them out-of-domain. We test on this out-of-domain data set. So this data set is completely synthetic. It's completely new. There is no data contamination and no overfitting. We can still see a performance improvement from our RL model compared to all other famous just large language models. It's like those large language models, they do not really know Dafny. This task is not really covered by those model. So this makes our task very interesting. Just it gives us a playground without data contamination to really test out your model. And then just we say in our pipeline that we do not use any human COT. And then we can still see the improvement from the RL. However, we do not claim that like learning without COT is enough for all reasoning tasks. It possibly implies just our current coding task is still too simple. And when we do out-of-domain generalization, even though our RL model is the best, its accuracy rate at pass at 8 is still below 40%. However, when we say just in domain, it's almost 90%. We can still see a quite big performance drop. So maybe when we want to do out-of-domain generalization, we will still need COT. What we claim is that currently our model without any human annotated COT just give us a playground where we can really learn the intermediate tokens needed through experience from scratch. And the second thing we want to mention is that we want to have minimal human prior, but it does not mean we have zero human bias. On the contrary, we think some level of human bias is actually necessary. Just imagine that if there is no human bias, then any combination of tokens will be treated equally. Then it will be a huge space for RL to explore. So it's not going to work. Here we list out just the human bias we still keep. So first, our training data is transformed from human written Python. And we use Tian encoder as our base model, which is pre-trained on massive human data. We also have a very limited supervised fine-tuning process because Tian encoder does not know Dafny at all. And at last, we have human design even on the correctness of formal statement, but we really pick out just what statement we need to verify. That's basically our project. Do you have any question about our project?
Yeah. It sounds a lot.
Okay,
Maybe
yeah.
what you want to talk? Yeah, any questions? Yeah, feel free to open your mic. And
It's okay. I still have just it's only halfway
oh, oh,
to the
okay.
talk.
Oh, okay,
Uh,
okay. But there's questions
I
if
just want to
you
make
want
sure
to.
everyone just uh 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 let me see this question. During RL training, is it like we do back propagation to predict the next token based on the best reward output? Uh, Still we are using autoregressive model. So yes, we are still trying to predict the next token. And if there is no other question, let's go into um, some open discussion area. As I mentioned at the beginning, just I want to really talk about the hardness we realized during this code auto-formalization task. So let's start from traditional RL. People start to wonder, like for Atari games, people start to wonder if we are really learning the rule, the underlying rule, or we are just memorizing some patterns. So there are some interesting experiments people conducted. The first one, people start to do some modification to the Atari games, like color change, speed change, stuff like that. And what people do is try to simplify the Atari game. So if you see the human performance, if you compare the first column and second column, you can see just the human actually perform better on the variation because the game is simplified. However, it's not the case for PPO. The second column still gave us a performance drop, a very obvious performance drop. And for the highlighted task, there is only color change of the objective. However, the agent is suffering from a performance drop. It's somehow implying, okay, maybe agent is just remembering the pattern. And we say maybe maybe the agent is just overtrained to this one specific task. How about if we train the agent on multiple tasks on the same time? So people just by different tasks, it's just mean it's still one Atari game like Montezuma, but people start to do different modifications, small modifications, and people realize, okay, if we want to avoid overfitting, blue line shows the training result, orange line shows the test result. If we want the test result to match the training result without overfitting, we need at least 1,000 of levels. It suggests us maybe do RL training. We should really train the agent on multiple tasks to avoid just the pattern memorization. Then for a large language model, are we doing pattern memorization or really rule-based reasoning? This paper analyzed transformer only. It's not really analyzed large language model. It's just analyzed architecture transformer. It focused on numeric addition. It leave a space, just some questions uncovered by the training set, and then test on that uncovered space. And the answer is negative. Transformer cannot really behave well on that uncovered area. So it's suggesting maybe transformer is again just doing pattern memorization instead of rule-based reasoning. This is going to be a big issue for code auto-formalization. As we mentioned at the beginning, like code will contain multiple algorithms, multiple data structure, multiple deduction process. Without rule-based learning, just how can we succeed in billions of code, billions of algorithms? So this just reminds us like stronger abstraction and composition ability it's a bottleneck right now for rule-based generalization. And what does abstraction and composition mean? Like temporal abstraction, an idea proposed by Rich and Doanna, just to say, we can combine a sequence of actions into reusable skills. And when we want to solve a new task, we just need to recompose these skills. And this high-level abstraction just narrow down those billions of tasks into a smaller set of skills. And like, this is one of my famous quotes by Professor Elizabeth Spelke, the possession of infinitely many concepts that were expressible in an innate language would lead to a curse of a compositional mind. When our human, we can summarize rules. It basically say we are doing some right level of abstraction and composition. And maybe we should also bring this ability to large language model. This is one point. And the second point is about effective exploration. As I mentioned at the beginning, just right now, we do not have a simulator anymore. Large language model is the simulator as well as the actor. And reinforcement learning, it's called reinforcement. It means it can only reinforce good behaviors. Just when an agent can already do good behaviors, RL can help us to focus more to sample such good behaviors more, but it does not really help the agent to generate such good behavior. And how to generate rewarding solutions is what we call effective exploration. I think this is a bottleneck for current LLM plus RL training as well. If there is no way to generate rewarding solutions, RL will definitely not improve your model. And let's see what skills, what techniques, what tools do we have. The first thing, exploration by randomness. And that's very low efficiency, but that's the only thing we have right now. We are doing entropy maximization, also per token level entropy maximization. That's the only thing we have. Can we borrow some tools from traditional RL? And what I figured out is possibly not. Traditional RL say we can do exploration by uncertainty or curiosity. Just as long as there is a state which is less covered, then it gives a high uncertainty. It's less covered, so it gives a very low confidence bound. It's less covered than it can reach the curiosity of the agent. However, the thing is, not in large language model, not all less covered states are interesting. Not all combinations of token are meaningful. Like in Dafny, not all combinations are syntaxically correct. And also there are countably infinite combination of tokens. It's impossible to cover all states as well. Then this thing, the exploration by uncertainty thing, seems not to fit for large language model. The other thing people have is called information guided exploration. The agent is asked to take actions which can give us more information about the dynamics. However, now we do not have a simulator. There is no dynamics anymore. We only have reward, it's correct or not. Then what information should we care? Like information guided exploration cannot be about learning the dynamics anymore. What should we learn? I think this is a very interesting question, and this is what I'm working on. Like, how can we ask the agent to generate solutions? The last thing I want to discuss is from to large language model, there seems to be a change of objective. Like for Montezuma, the agent focus on only one task. or just the variations of this single task. And the agent almost always start from the same initial state. And it try to just the agent start from some initial state, and there is a distribution of the initial state given. The agent just to say try to maximize the cumulative reward given this initial state distribution. When we go to large language model, now we are working on all kind of code snips. It gives us a more diverse set of initial states. Instead of initialized at Montezuma only, now we are initialized at like all kind of tasks at the same time. The initial state distribution is much richer. And also, we cannot say, okay, maximize your cumulative reward with respect to this initial state distribution anymore. It's not like they are just if your initial state, just the initial state distribution gave a weight over tasks. It's not like you can weight my tasks less than the other tasks. Like you cannot say highly likely for most users, they can get a correct answer. But maybe for you, for your specific question, you don't have enough weight in the initial state distribution. So you are not guaranteed to get a correct answer. That's not how this business should work. It's like if we say reward is in 0 or 1, it's like for all initial state, for all tasks C, the large language model should output the correct solution. And that's what people call exact learning. What does this new exact learning framework, new task, mean? Like it gave us a burden on data synthesis. Like if there is an initial state distribution, a task distribution, then we just need to synthesize data according to that distribution. But now we want to say, okay, all data points matter equally, all data points matter equally. Then how to create the data? This become a question. And the second thing is this exact learning gave us one more reason to do formal verification. If we want our solution to always be correct, then maybe a good way is to say, before outputting your solution to the user, pass it to the verifier first. If the verifier say, okay, your solution is correct, then give it to the user. Just this formal verification thing just ensure there is no hallucination in the solution, ensures the correctness of the solution. The last point we want to say still is about this formal verification thing. This no hallucination, 100% correctness is very important for AI safety. If each time there is only a small error, and this error accumulate along the horizon, it can cause us a big trouble possibly. And also if the agent always have the probability of making an error, say each time it has a probability of 1 over a billion to make an error, the probability is very low. But when you ask the agent to generate for 5 minutes, I forgot the exact number, but just it's like almost sure every 5 minutes there is going to be an error. So we really want just a 0 error, exact learning, no hallucination thing. And then another thing is, another reason why we want to choose formal verification is about the scalable oversight. Some people claim that AI will reach human level intelligence by 2029. I feel just the current AI already succeed my ability in coding and math. Then just how can human just supervise an intelligence superior to human? Just people call this task scalable oversight. Just how can a cat supervise human? um, so a possible way is that we should give up checking the correctness of each individual, of each task. We should really build up a system which can give us procedural correctness so we know the solution is trustable. That's why we just think formal verification maybe is a key element in building up such procedural correctness. And that's why just let me find the slide. That's why we say probably we should pay more attention to this verifiable coding agent, not only because it's an interesting task without data contamination, it's clear reward, so it's good to test out your model, not only because it's some task people say, okay, it's going to improve general reasoning. Maybe it's some fundamental thing that will really just be a keystone for AI safety. And now that's it. Thanks for listening.
Yeah, yeah, sounds good. Just I thought you finished. So yeah, sounds good for the wonderful talk. Let's see if there are questions. Yeah, feel free to open mic if there are questions. Yeah, maybe first let me ask a clarification question. Yeah. How about you? Yeah, can you say that again for uh the partial order of the subset, right? Partial order. You
Oh,
have the partial order. Yeah, that concept may be somehow involved for many people.
oh, okay. Like we say statement A and statement B. Uh, um, Let me see if I can tap down something. So it's going to like we have a statement like x larger than 10 and another statement like x equal to 100. And
Okay.
we know just the x equal to 100 is a stronger statement than x larger than 10. Then just mathematically, like x equal to 100 imply x larger than 10.
Mhm.
Uh,
But it not
so
always.
this statement, just
Oh,
like
okay.
if
Yeah.
it's a subset of
Okay.
the
Yeah. Yeah.
second,
Yeah. Okay.
yeah, if it's a stronger, it's a subset of the second condition. It's always true. So
Okay.
that's what we are looking for. Just our generated post condition, just the generated post condition should imply the ground truth post condition. Because we say if it's stronger, then it gives a narrower range for output. It more precisely just a small range, like you see, the output should equal to 100. It more precisely describe the code behavior. So we say it's better.
Okay. Uh, okay. Yeah, makes more sense. Thank you.
No
Um,
problem.
yeah, let me
Uh,
see. Yeah, I think there are questions.
there's a question about the learning process, different from the reinforcement learning from a game. Is it like because there's not really any discounted rewards because you are just going from one state to get a reward, and then you do back propagation. It's like uh, you are just like generating data on the by the LLM itself. You give it a feedback and it's trained based on its own output.
I think this discount factor is a nature thing. of any task. Like for Atari, like when RL people report performance, we can do a check here. No one report the discounted reward they gain. Just people only report the
Yeah.
cumulative reward. So this discount factor thing is more like a tool people use to stabilize training. Like in traditional RL, there are so many rewards, just so many per step in dense reward. Just if there is no discount factor, the sum of reward will go beyond a reasonable range and make the training very unstable. However, for large language model, if we only have outcome reward, either like here, we only have outcome reward, either 0 or 1, then discount factor is not needed anymore. I think like
Yeah.
just
Yeah, I mean, there's no like
that's
future state at all because it's not like not like in a simulation where we have different states. We have only like one or two states, and so it's a bit, I don't know, feels a bit uh
yeah, I would say just like right now in large language model, I don't think we really need this discount factor.
yeah. I'm not saying like discount factor isn't required. I'm just saying like is it because that we don't really have a system where we can set all the rule sets. Oh, basically, as you said, we don't have a simulation, so there's limitations of uh what we can do with RL on large language model.
I don't get it. Do you say just without
So
this?
so it's like in a game, the agent can master the game actually from most starting points, right? Uh, in a lot of cases, and it kind of knows all which state because it develops all which states is to do which actions because it understands all the space in the simulation, and for RL on LM it's different in terms of um, you don't really have a system anymore. You don't.
Are you talking something like say world model or rules or like game rule, right? The games has rules and um yeah the code but the code have syntax. So can we say syntax are the rules?
Yeah, but it doesn't seem to be very generalizing on things. F- for example, if when we are generating the code task in this case, I think it's hard for the agent to like generalize well on out of domain tasks. So, all right, I'm just
Mm. I think that's the challenge. Just like you mentioned, multiple things like um uh like LLM does not have this word anymore. Um uh it's mm, like it's to me like just it's just the modeling issue. Just someone mentioned at the beginning, just the LLM is next token prediction, and people try to model it as a Monte Carlo decision process and then use RL. Just so like uh the each token you generated is the action as well as the next state. So I think just the uh,
ah,
RL, just the framework still work for uh, large language model generation somehow. That's why we can apply RL.
hmm.
And
Yeah, I
then you
think he
also
also
mentioned
asked a question about generalization. Yeah, but my understanding is since we are using like neural networks, neural networks can be help generate generalize somehow, and it depends on how much data we are learning, right? How much data and what kind of recoveries of the data. Yeah, yeah,
Yes, like it's really hard to define what is generalization. Like if it's like new data, never seen by the training data, but it's still uh like similar type of data, just a similar, just like for our training data, we call it in domain. They are just all like some numerical manipulation, but we change the variable name. Just in code, we can freely change the variable name or the order of code. Then for this kind of generalization, our model do very well. But when we want to compose multiple functions together, or we introduce some completely new algorithm, like previously the model never trained on dynamic programming data, and now we want to say, can you generalize to a dynamic programming algorithm? For those compositional generalization and out of domain generalization, just I think it's still an open question. Like the model does not do very well.
For deep learning generalization, yeah, different new cases, new scenarios. But for I think for animal learning, if you see those scenarios and you learn from them, then maybe you can do it better. And yeah, it's a little bit tricky for deep learning, right? I think.
Yeah.
But
Um,
sometimes I think important thing is to, for example, for games like chess and Go, if you can learn a very good policy, that's good enough. We don't care too much about generalization. And for code, if you can, if you have all those all possible scenarios, that's also fine. But for game for code, the space should be very big. State, action, and all the cases too big. But yeah,
I think even for Go, it's like sometimes we expect a person who is very good at Chinese chess, that person should also be good at international chess. But that's not the case for RL agent either. Just the generalization is still an issue.
yeah, that's true. Yeah. Um. Yeah. So, is this result helpful for code generation? It seems you are requiring some code, right, to start.
Yeah.
It seems the input is a code, and then you do say Python code, and then you translate to Dafny, and then do the verification.
Yes.
So in this case, it is work helpful for code generation. I mean, the input is maybe English, and then generate code.
Uh, do you mean like
I mean,
if we
if your paper is helpful, somebody want to do code generation, generate code from English requirement. So is this work helpful for that task or not?
I think this pipeline just should is quite general. Just like for code, um, as long as they can synthesize an infinite amount of questions, and for code, they have compiler to verify the quality, and then they apply RL. Just with, I think they can reuse this pipeline, and they will face the same generalization exploration issues as well.
Okay. But the first step is a code, right? You have some code, the first step.
Just for us, just those is just a synthesize task, synthesize input. Like they need to synthesize enough user query, natural language queries.
Oh, okay. Oh, this is the first step is natural language. Okay.
Yeah,
Okay. Okay. So that's like code generation. Okay.
yeah,
Yeah. Let me see. Other more questions?
Can you go back to the three state or like the slide 7? Uh, I was not really, I was a little bit lost in here. So, like, how do we have a verifier and the code? It's like if you fully understand the algorithm, you should write the code and the verifier at the same time.
The verifier is given. It's
Oh, it's
like
given.
we should write out the specification labeled in blue, or sorry,
Oh,
labeled
those
in
are the
gray.
specification. Okay, okay.
Yeah, yeah, write out those things at the same time. And then this whole complete output will be passed to a Dafny verifier. Dafny verifier will say, given this code, will those specification always hold?
Oh, okay. So it's like the LM also generates the code, and then it generates a verifier, and it goes to the specification, and then it goes to the verifier to verify the code.
Yes. Like if we can get like for example, just like if user is not express their query in natural language, just
Okay.
let's imagine just I'm a user who can directly write out my query in formal language, and then just if the agent generate a code which verifiers say okay it's verified, then I can 100 it's 100% guaranteed that the code align with my query, it align with my intention. That's what we want to do. Just the code exactly capture what the user want. So, but the thing is, usually the user asks questions in natural language. Then it's important that the agent can help the user to maybe refine that query so that the query is complete and the query can be translated to formal language.
Okay. Okay.
Yeah. Yeah, so just now you mentioned several reinforcement learning techniques. So you are working on those, so uh,
Yeah, we are working on like COT design. Just can we design COT?
COT, okay.
Can we maybe realize? Can we what kind of temporal abstraction can we do? What will be the effective exploration technique? Like if it's exact learning, just how should we sample data? How just because we mentioned before, like our input is synthesized, then just which data should we synthesize to further improvement to further improve the agent to ensure that just it's another question we are focusing on. Just it's a huge group, so many research directions.
Okay, so all these you are working on. Are there some results already or
Not really.
okay. Yeah.
Yeah.
Yeah, I was thinking about, I think there's a lot of dominology in the code. For example, AST, abstract syntax tree, those kind of things. Are you trying to leverage those dominology? I think those dominology they're perfect, right? They're perfect, and maybe they're helpful.
Yes, we are using those domain knowledge. Um, just a very hard thing is for specification. Like now we are only present a very simple code. The specification has only 3 lines, but usually just for a complete specification for a hard code, it may contain the specification itself contain like already just 20 to 30 lines, contain multiple lemmas and functions. The issue is for specification, we cannot abstract the we cannot get the AST, we cannot get the abstract syntax tree. Uh,
Oh,
we can only have the syntax tree for the code, not the specification.
okay.
That's
Why you cannot get AST for those specification?
just when we just interpret Dafny to an intermediate language, just there is nothing to support us to extract the abstract syntax tree.
Okay.
I think just definitely just their intermediate language somehow they just there isn't any useful tools to extract that out.
Okay. Yeah. Uh, yeah. So yeah, there you already have lots of field work to do, right? Like many refining algorithms, many refining directions. Uh,
Yeah.
um, yes, I think that's interesting. Let me see. What else? Are there more questions from the audience? Yeah, what do you think by this quote? What do you mean?
Uh, it's like just the human has just our natural language has compositionality. Like we have infinitely many objects, infinitely many concepts, but usually human can describe those concepts in plain language. It means somehow we uh, make an abstraction of those concepts, like fruit, like all the
Mhm.
objects we have fruit, we have uh, animals, like we make abstraction and then we recompose those abstraction to express infinitely many concepts out. So human somehow it's born with a compositional mind. And so uh, how can we just really make our agent to have such ability as well to do uh, such like just those how to get skills, how to recompose skills like that.
Oh, okay.
Is it COT? Or is it really not
That's
really?
one thing. Like COT, like COT is like when we see on the right hand side, COT is exactly summarizing the rule. However, the issue is current COT is human annotated. It means for tasks like math, like addition, for tasks people have annotated. We know the rule. We follow the rule given by the human. But for just the tasks without human annotation, um, just we don't have a very well defined COT either.
Yeah.
But also COT may be a heuristic, right? It may not be optimal. It even may not be
Right.
correct. So COT is not fully reliable.
Yes, and I think people some right now try to just directly do some mechanical interpretation, just to do some analyze of um uh, agent neurons, and they want to see if there is any composition thing going on among those neurons. I think those kind of work is very interesting as well.
Okay. Yeah. Um, but even with those interpretability, I mean COT, is a some technique, and when people using COT, and they give some those channel sort, but it may make some mistakes in the COT. So right, it may make mistakes sometimes. So that's a problem. I think it's valid for code and for your verification. Something wrong may not be good, right? If something wrong at the beginning at the COT level, then it's hard to fix it later on. Something like that.
Oh, at the beginning, we have another project. We try to write COT in formal language as well so that we can verify COT. But just we realized just such high design COT has no improvement for performance at all.
But
That's
it's something like COT is I think COT is close to the policy we want to learn, right? So when people write COT, people try to approximate the policy. So there's a circle, there's a chicken egg problem. So people don't know a solution, but people want to write COT to help the language model to find the optimal solution. So I think that's a problem. And also I think also for like procedure reward, I think that there's also something wrong. Yeah, I'm a critic. So, when we want to get procedure reward, we want to give reward to each step. Uh, if it's not well defined, then actually I think the procedure reward is close to value function rather than reward. So that's something we are looking for. There are some papers talking about outcome reward or procedure reward. So I'm not quite sure they are the good direction to go. Yeah.
Yeah, just like people just training stuck in that loop.
Yeah, it's kind of like a chicken egg problem, right? Something like that.
Yeah, yeah,
Okay.
yeah.
Yeah. Maybe let me see if there are more questions. Oh, maybe if no, let me ask one more question. Yeah, how do you think this verification uh will be a part of language model especially for those big ones like say Gemini, Claude. Do you think they will take verification as part of their project? And will
I think
I mean
somehow
is it easy to scale this verification into the say cloud level?
to what I know, like to my knowledge, is like those big companies, they have some formal verification tools already. Uh, but it doesn't seem like they apply it to their coding agents yet. Um, and I can see Amazon is like right now is hiring people for formal verification. So I would say just it's an active direction. Uh, like it's definitely a
Yeah,
better
yeah,
way
yeah, yeah, yeah.
to formal
I think
verification of coding.
yeah,
Uh, the only thing is maybe they are formally verifying their just their own code, but they are not verifying when will they decide to verify their generated code.
yeah.
Just what
Yeah,
yeah.
I was read an article from Amazon people. They are running a cloud, so their system should be very robust. Otherwise, they lose lots of money, lots of customers. So they want to verify the cloud system is, as the bugs as few as possible. So, but maybe I think there's a trade-off between cost and the robustness. Maybe the problem is whether learning models need to be this kind of robust because verification will be costly to do, right?
But one big company, just one companies want to use those generated code. Each company themselves actually formally verify their own code.
Okay. Yeah. And maybe depend on application. If they want to apply this to like SpaceX, then they have to verify everything is correct. Otherwise, the cost will be too high, to have a bug.
Yeah, just what I mean is like right now the formal verification happen on the customer side instead of the business side. It's instead of the producer side. So it's just uh, uh, maybe that will be the ecosystem at last. Just every company who use cloud code, they have their own formal verifier. Maybe that's the current situation.
Okay. Okay. Yeah. Yeah, that's great. Do you have some last word or summarization of your talk or something before we finish?
Maybe just pay a little bit attention to um, AI safety. Like one, just maybe we should really think a little bit. Just how should we get along with a super intelligence? Like if we are the cat, how should cat get along with human?
Oh
Just
yeah.
how can we ensure just we can still independently think? How can we still ensure our resources like that?
Yeah, yeah, I think that's a good point. I once went to the attended the computer aided verification in Montreal 2024. When I talk with those people, so I'm not quite a verification people, but so I talked with them and I said something like, yeah, just like you said, safety is a very good point for verification people to sell to the other people from other fields. So verification is a good tool to make sure the system is safety. Yeah, that's a good point. Yeah.
I feel
Um,
Rich has a similar point as you. He always say like anyone told you to be fair, to care about AI safety, is the person who want to control you.
oh
but
yeah, yeah,
but
yeah,
but somehow I think just we shouldn't be af be afraid, but we should really think how we will get along with the super intelligence.
yeah, yeah, yeah. Yeah, yeah. This year I follow him closely. So he has a talk and he talk about decentralized collaboration rather than centralized, for example, for safety. And he also actually he wrote an article or blog some time ago about verification. Long time ago,
Yeah,
maybe 20
2000,
years ago. Yeah.
like 2000.
Yeah, I think he said something like if it's not verified, then it's not correct, something like that. Long time ago, yeah. I think when he was kind of
Yeah,
yeah.
yeah. Thanks for this nice conclusion.
Yeah, that's great. If there are, yeah, maybe just last call. If there are more questions, I'll just count three, two, one. Okay. Okay. So yeah, thanks again for Fengdi for the one more talk, and hopefully you how make this work, especially verification more scalable and be useful for many projects, many product. Yeah, I think that's a very important thing, verification. Yeah. Thank you.
Yeah, yeah. Thanks.
Yeah, and also thanks for the audience to come. Yeah. Okay.
Yeah,
So
thanks for the discussion.
yeah, see you next time. Yeah. Okay. We are and